Welcome to part 2 of BackBit Impawsible. Now, if you're just joining us, why are you watching part 2 first? Go watch the first one. Here's what you missed. I show a little clip of my latest project that I'm so proud of, where I have a Commodore 64 video playing at 24 frames a second. And it's done because of the magic of multicolor character sets. I made my video frames as multicolor characters instead of a bitmap. And previously, my earlier project called Wolves on the BackBit, I was, I ran into a bit of a roadblock because I wanted to do this, 2 years ago, but I was unable to convert the bitmaps I had made at the time to multicolor character sets. And there's one good reason, and here it is. Yes, it was the RetroPixels program, because I used that program, somebody else's program, to convert all of my candidate frames into multicolor bitmaps, into koala images that I used in this project. But the thing is, now I'm stuck with the decisions that that program made. You have one global color for the screen and 3 unique colors for every cell. Well, in a multicolor character set layout, things are quite different. You have 3 global colors common to the screen and 1 color per cell that is limited to 0 to 7. And with those restrictions in mind, you've got what was once somewhat wide open and it became very restricted at the end. It's like a photocopy of a photocopy. I was dealing with a problem that I knew was going to be awful. And in the end, I gave up. I realized the biggest hurdle, if I ever pursue such a project again, is not to rely on the RetroPixels program. That program is great. Like, if you just want to screw around and bring something in and, flip the sliders around and see what it looks like in different things, you'd be surprised. Wow, it does it so fast and beautifully. And, I love it. I really do. It's great for monkeying around. But the big problem was that I relied on it. And the other hurdle was, think RGB. You've got 3 values, 0 to 255. Think of a cube, X, Y, Z. Each value is a axis on this cube. That pinpoints where this color is for that pixel. Now, here's the really scary part. Imagine you got to find, say you got a pixel of whatever value, and you're like, well, what Commodore color is closest to that? And suppose you take every Commodore color and you come up with a RGB XYZ value for them, an estimate, who knows, maybe you can look it up somewhere and find one. You need a way to find out mathematically this pixel is closest to which Commodore color. You're talking 3D Pythagorean distance formula, which is basically the root of the x difference squared plus the y difference squared plus the z difference squared. Are you freaking kidding me? That is insane. But there was, I didn't realize that at the time, but later I'm just like, oh my God, I needed this. There was a thread on the Lemon forums a couple years back, and I was excited about it because, it's math and it was cool and I loved the idea. So I jumped on in, and even though I don't understand how the routine works, I was able to get through it enough to where I knew I could make use of it in the future, and that was golden. And long story short, I knew I could figure out the distance between 2 points in 3D space in about 1,000 machine cycles, which is pretty quick. But as luck or skill or I don't know, what have it, I haven't counted in a while because I did this last summer. This is 2024. I think I actually got that down to 200 or less. An insanely fast distance algorithm. It's not really an algorithm, it was more of a fudge, but it's accurate and it worked. Take a look at my lovely crude model. We have 3 axes. We have X, Y, and Z. For instance, black is close to 0 and white is close to maximum. And every color is somewhere in between. Now, in this instance, this is the color choices that the program's going to have at its disposal. We have the locked-in colors here of number 10, which is pink, 13, which is light green, and black, which is close to 0, right? Whatever. It's adjustable. And every other color, these are the only ones that it has access to. As you can see, what do we got? We got color 1, 2, 3. Sorry, I didn't have a cyan in my kit. 4. What do you got? 5, 6, and 7 over here. Yes. Now, purple, the little bastard, it is, well, you'll see it is very powerful. A lot of colors resolve to purple. So to fix that, I actually changed the value of purple to be down here, hiding behind black, so it never gets selected, right? That's pretty cool. Now, but for the time being, I do have it where it originates. Now, here's how well, when you have a pixel in question, it could be anywhere, right? Let's see. Here's our mystery pixel. Jab it in there. There we go. What color is that? I don't know. So what we do is we use our little tricks here, and we find out how far away it is to every one of these things. And that's basically it. The lowest value is the one it's closest to. Now, but you can't have it be closest to this one and this one, like a different pixel in the same cell. But we solve that problem later. But what it does, first of all, it checks the 3 that are locked in against this one, pink and black. And whichever one is closest is the, quote, best for that pixel. So it remembers it, right? Say it's closest to this one. So when we do further tests to qualify, a distance has to be lower than our current best that we know we're going to count on. And if nothing beats this, then it does get resolved to that. But if it gets resolved to this, well, it may not necessarily get that because other pixels might lean towards this one. At which point this will get resolved to green instead. It's kind of cool. Maybe I'll show a bit more of the code because this model was a big waste of $5, I tell you. And look at all this leftover clay I got. Yeah. This model sucks. I'm sorry. Yeah, I'm sorry about that little suck fest there. But instead of showing you the code that does all the magic, let me tell you about the math. So let's start with 2 sample points right there. And so we got to figure out the distance between them. Well, lucky for us, as you can see, they're rather low numbers. Why? Because now we're dealing with XYZ values that are only 5 bits in size instead of the original 8. So instead of 16 million possible positions on the cube, there are only 32,768, which is still, quite a wieldy number. However, as you can see, each axis is only, 0 to 31 now. So you've seen the equation. Yes, there it is. That's very intimidating. But okay, so the beauty of this is, and you'll see why it has to be beautiful in a moment, everything is done with tables. So our X difference, check it out. Boom, there it is. It can only span from 31 to negative 31. So that's pretty easy to do. You just have a simple 2 pages of lookup space, low byte, high byte. That will take care of everything of pre-calculated squares. And you do that for all 3 values. Use the same table, of course. So the maximum size for each of these squares, 31 squared, is, what is that, 900 and... Oh, I should know this. 961. That's right. So 961 for each component, and, well, 961 times 3, 2883 is your total. So use a different table of pre-rooted calculations. 2,883, well, I have 14 pages set up, so I had more space than I needed because I dedicated 4K for these tables. And so that was it. I was able to easily add up the three values and reach into my table of pre-made squares, and there's the distance. Easy as pie, isn't it? Now, while it has been a year since I did this code, so I'm digging in, I'm playing digital archaeologist, and I realized thanks to Dithering, there was a bug baked into my tables and stuff, because thanks to Dithering, the 31 is not the maximum. It could have been as high as 30, possibly 37 or 38. Even though my table of squares would have easily handled it, because my pre-made table of squares goes from 0 to 127 and then 128 to negative 128 to minus 1. But you add up 37 squared times 3, and it actually extends beyond the 14 pages of pre-rooted values that I allocated for this problem. However, I don't think it ever reared its ugly head at all, which is good, because that would have sucked. But the bug is there, and I'll be more careful next time. Maybe I'll show the code at the very end of this video. You can look at it on your own time if you want. But Dithering, well, at first I did it rather complicated, more complicated than it needed to be. Let's skip that part. Take a look at my Dithering table now. See? 32 simple values, and I basically take each RGB component of the cell in question, and I add its associated value to each of the RGB values. So some values get brighter, some get unchanged. I don't even have any negative ones. I've already tweaked the data, so everything's just an add. So as I'm bringing in the data, I add my dither value, and it's so easy. It's so fast. I'm so pleased with it. Impaw 9.7, I call it, or it was basically the very last version, because after this, the bitmaps are done. They're locked in, and I don't need the Impaw 9.7 anymore. But so that was that. So there's something else I wanted to tell you here, rather important. Okay, so you've seen the calculation. Now here's the scoop. You got to apply this to your. Let's start with 1 pixel. Here's our pixel. Yay. First we check it versus the 3 locked-in values that I've pre-selected. And then you have to also check it against all the other low possible values that might be in that cell. Because you don't know which of those 7 other values is going to be the color candidate. You don't know yet. The whole problem here is figuring that value out. You got the 3 locked in ones. Well, what's the 4th going to be for that cell? And this is insane. The amount of math that has to happen here. Well, check it out. Okay. First, now I wrote a little program. I held the camera steady because I'm not ripping this onto video just for this. But take a look. Here are I only fit 23 pixels in the data that you see here. The rest are just off screen. But take a look. These are the values of the distance. I did a 2D version just for fun. Just bear with me here. This is a 2D mock-up. The same calculations take place, but look at the data. This is how far each pixel is from the black, the pink, and the light green components. And once we have those values for all pixels, to optimize it a bit, because it'll come in handy later, let's find the lowest value, the closest one. This is the backup, just in case we use that particular color. But for every one of these pixels, all 31 of them in the cell, we have to compare them all to white, red, cyan, purple, green, blue, and yellow, all of them. And yeah, okay, so we run this algorithm a whole bunch, a bunch of lookups. But, well, take a peek. This is how much, look how many times it needs to do this. I'm glad I was able to use simple lookups to do this, because, wow, it is insane. I can't remember the exact math. I figured it out once the other day for fun. But I think over the course of the video to come up with whatever, I'll tell you in a second. But it has to do this calculation, this table lookup nonsense, approximately 400 billion times during the course of the video to figure out that fourth locked-in color for every single cell on every single frame. But anyway, so back to this. There we go. Well, what we do is we pretend, well, what if we use white? What if we use red? What if we use cyan? And it goes through that, and it basically goes, okay, for every single pixel, say we're going to use white. It's either going to be white, if it's closer to the pixel in question, or it's going to be its fallback color. Either way, we use the lowest value and add it to our tally. And we add them all up for every possible pixel choice. And as you can see, blue's the winner here. It's the lowest value. I mean, in my sample map, yeah, the pixels are all over the place, but whatever. It's usually not this close of a race. But once we have our blue is our winner, now we have our fourth locked-in color. So there you go. Simple as this now. There's our fourth choice. So let's finalize this stupid pixel. Not the pixel, the cell. Everything that's closest to black, everything that's closest to pink, light green, and now blue. And take a look. Take away our locked colors because they're not really plotted. They were just mathematically there. Here are our 32 pixels now. See? I love it. I love how the distribution works. It takes the most favorable possibility and makes it happen. And after I had this logic in place, it was such a relief because I can trust this code. It's great and it works well. You feed it 4 different colors, well, 3 locked-in ones, and it does the best it can. You'll see in my sample in the clips, I haven't shown you any of the clips yet, but as you can see, early on I make mistakes. My early clips are a bit too bright because I have my Commodore color presets too low. So all my data is reaching up towards the brighter colors. And I thought, that's not very good. But as time goes on, in the week or two it took to do this, you'll see the colors improve. I think I tweak my dithering a bit. In the end, you'll see, because I mean, that's why there's a video here. I better shut up and show you this stuff. But by the end of this video, I will have my bitmaps done, and they will be ready to go for the next step, and that is going to be an even greater challenge than what you've just seen here. So anyway, yeah, thank you. Now let's get to the clips. Here's the source code as promised. However, the video clips are going to have to wait for the next video because this one's running long already and I don't want it to be 30 or 40 minutes long. Nobody watches those things. Well, till next time. And if you have watched up to now, you get a good feel as to what I'm up against, and I thank you for that. I really do appreciate the fact that you sat through this. It took a lot longer to make this particular video than I initially planned, thanks to all the little cutaways and overlays and all that stuff, but this is probably the most work I'll ever put into any one of these. The rest of them are mostly just clips, starting with the next one. But anyway, thank you, and if you have any comments, feel free to leave them because that always helps the algorithm, But yeah, if you just want to look at the source, well, you could have hit mute and shut up, my furry ass, but it's probably too late now. But anyway, I'm going to let the last frame hang for a bit because, YouTube's going to stick its title cards and stuff over the source, and I don't want it to cover anything up. Anyway, thanks for watching, and till next time, I'm Luke Darksnout.